Hello and welcome to our presentation where we explore the depths of STM8, a microcontroller from ST Microelectronics. The title of this presentation was chosen by Sergi Pancake based on the fun we had working together in this e-waste project, treadmill. So today we will very briefly see why it's important to fix and improve the STM8 support in r2. I will show a couple of tricks to productively reverse engineer the circuit schematic for our particular hardware target. And we'll also see how large language models, so-called AI nowadays, assisted in generating great decompilation that outperforms most traditional decompilers through R2 AI and decai. So in the interest of time, I will not deep dive into the particular features of this 8-bit microcontroller. Any of you can look this up fast by your favorite search engine or AI bot, so I will not entertain the fine details of this particular 8-bit microcontroller family in this presentation. I will just say that it's a very common microcontroller and is very price competitive given its features. And also it has been around for a long time, so it can be found in many consumer devices nowadays. But which consumer devices, you might wonder? Well, here's your typical and cheap tankless water heater running on an STM8, as this teardown video from Diode Gone Wild, famous YouTuber, shows. Most common functions that our low-power microcontroller does are controlling power regime of IGBT transistors, driving peripherals such as LCD screens, and reading values from sensors such as NTC temperature probes and other boards connected to I2C buses, just to name a few. The microcontroller is also capable of outputting PWM signals, for instance, which can drive motors. So you're not convinced about how common this thing is in the wild yet? Here's another YouTuber, Buy It, Fix It, showcasing a broken Nespresso coffee machine, where the STM8 microcontroller in the picture decides if you will have coffee today or not. That particular board will also flash some LEDs to inform you while sending some commands to the rest of the appliance. Every appliance can have many STM8 microcontrollers integrated inside, talking to each other. By now, you should start seeing the amount of chips running our everyday lives. Possibly more than Windows and Linux installs combined. Food for thought. So here's another example that literally hits home. This is my current washing machine. And of course, I opened it up for this presentation. Let's have a look inside. Yep, this is the board, and then these springy things are touch capacitive buttons, and those discrete LEDs are what you can see in the panel times, programs, and different presets. Those connect to different boards, etc., etc. So, who is running the whole show? Of course, an STM8 microcontroller. So you see where the rabbit hole goes. And they even have automotive versions for this chip, so you can even find them in your car, or even a dryer probably, which if you look closer, it's actually asking to be reversed. Ah, Jokes aside, I think it's important to have sharp tools like Radar2 to reverse engineer and eventually repair any and all devices that you own or find in the dumpster, like my case. So in today's episode of Let's Reverse Engineer what I found in the trash, uh, this treadmill has two PCBs, one that displays things on this black rectangle, namely time and how are you doing with calories. The other one controlling the 180 volt motor. Both of those PCBs have STM8 microcontrollers on them, so it was luckily straightforward to dump them. Just with an ST-Link V2 probe, I was able to retrieve not only the firmware but also the EEPROM and even the active RAM on those devices. And Then I went straight to the Rather2 issue tracker, where there was an existing STM8 architecture support issue that it was long-standing from 2020. Then I added my own observations on the quality of the disassembly, and then Pancake jumped in. And here's Pancake. Here's how he looks in real life. So just say hello to him when you see him. So he kindly responded several of the issues and fixed a few bugs, but it was not enough. And then we followed up after that issue was closed. But before going further, I would like to warn about some challenges with anything you find in the trash, and in particular this treadmill as well. Um, so one of the boards has an RF microcontroller that we will see later, but unfortunately, not no dedicated 2.4 gigahertz controller was found at the site when I found this device. So there's no possibility to just leave the traffic that came from that remote controller. That's off as a potential vector of making this thing work again. Then again, there's no guarantee that this device works to begin with. So this talk is mostly concerned or centered about or around the STM8 support for Rather 2 and what we can do with it, not necessarily as a like repair kind of talk. And there's also the typical warning about 220 volts. This is an appliance that not only has this hazard, but also it's not very well isolated and protected, just to save costs. And myself, I have very limited time and space. I don't usually do this kind of work in my day job. But let's go anyway. Let's see how far we get. So since we are in RadarCon, let's try Ghidra, right? Just to annoy Pancake a little bit and rile him up. So can we try Ghidra? Yes, we can. We have like this STM8 plugin support from Saulenka. Kudos to him or her because he really managed to get a really good plugin going on. Um, but unfortunately, the second biggest function on this firmware fails with this cryptic error, low-level error, overlapping input var nodes. So the decompilation is not possible for this big function in Ghidra. Also, this third-party plugin installation means that the upstream support is not there yet, although there's an open issue from 2021 that is still ongoing. Um, they claim or want to add pretty much the whole family. So when and if this goes merge upstream, this is going to be really interesting to have all those families supported. But this is not the case at present. And this issue hasn't seen much movement either, unfortunately. With Rather 2, you have support from the moment you clone Rather 2. It's a core plugin, so you can play with STM8 right away without installing any plugin whatsoever. The like Binary Ninja is a little bit worse. It doesn't even have community support for this architecture. But well, I mean that's how it is. It's not a criticism. It's just the way it is, and as well, there's it's a community effort. So sooner or later, it's gonna show up, and this is also kind of like a call for this support to get worked on further, and encourage those maintainers that initiated those plugins to finish them because it will be interesting to share and compare results. So here's a picture of the display board of the treadmill. As I said, it shows the different digits and how many calories or kilometers you have done. Um, as always with any hardware, only having a firmware dump and like disassembling and decompiling, it doesn't help a great deal because you also have to be aware of which pins are connected which devices, right? Otherwise, like just the naming of the pins is not going to help you much in determining function. Sometimes you will be lucky because those pins are already like pre-selected functions, so it's easy to infer the function, but it's even easier to have a little bit more knowledge on how the actual board works. And here I did a little bit of like drawings on which components are which. Here's the STM8 part, uh, which the firmware of which can be downloaded through these pin headers on the board. There's this like your typical jelly bean low dropout devices to stabilize the input voltage to 5 volts. As well, there's these shift registers, which all they do is just sequence the information that comes from the microcontroller into all those discrete LEDs, so they can display a number, and that is programmatically easy to display numbers and different information on the display. Then there's also this interesting part, which is the RF 2.4 gigahertz RF remote interface, for which remote we don't have, as I mentioned before. Um, you can tell by the squiggly antenna, onboard antenna, um, tuned to 2.4 gigahertz. This is a close-up of the same chip, and a possible way to go and make this device work is to simulate the input 2.4 gigahertz commands. But we have the problem here is that there's no easy way to explore this space unless you have prior knowledge on which commands or how do they look like, or which modulation does this chip use, etc. There is a datasheet for this chip, and it's a 8051 core processor. Uh, Today we are talking about the STM8, so this could be another fun adventure that we will reserve for another time. Then there's the other board that essentially controls the 180 volt DC motor that moves the treadmill itself. I also annotated the overall function of the different pins. So you have like the 220 volt input from mains on your home, and then the output is here in the motor. And here you have the STM8S003. This cable comes from the display board, and it's optically isolated with those two components. The programming header I used to read out the information from this microcontroller is here, this 4-pin header. And then you have the power components that have like this big dissipator. So you have the full range rectifier, IGBT, and diode, and then a power factor correction from mains, and a relay that clicks and interrupts the mains voltage when the device is not in operation. And so begins the reverse engineering of the PCB itself. It takes some time, but eventually I managed to figure out how the display board is connected and also how the control board is laid out. To do that, you can go in a couple of ways. One is with your multimeter, just probing and figuring out those connections and drawing them in KiCad. But I prefer to just put the boards against sunlight or against a bright light. Let me explain what this means. So look, it's really simple. You just have two pictures of the PCB, one on top and the other at the bottom. And then you have this opacity slider. And then you can see when you superpose them correctly with the correct solutions, as we will see later, you can easily trace where, for instance, different bias go. Like, let's say we want to trace this one. It goes down to this diode and then back. And you can do that for uh, more occluded regions, and it's going to be much faster than just probing those things individually by yourself. Really tedious to just go with the multimeter to do all this. Just make sure that you align those landmarks of your PCB against the different layers, like you see here in the pictures. And then eventually you can even script GIMP with script-foo, which I provide. Then this will essentially slide the opacity slider for you. Sorry for the shameless plug, but this article from Hackaday is how I managed to take much better pictures, higher quality pictures with good illumination, Nikon camera with a specific lens and a different distances, so you can do stack ups and techniques that allow you to have PCBs much better suited for this kind of fine layout reverse engineering work. So if you're interested in knowing how a new architecture comes to life in R2, I've compiled these different pull requests that we worked together with Pancake, and mostly Pancake, since he is very knowledgeable about R2. Put together those bug fixes as we were discussing them, and I was finding kind of issues with both the disassembly and the decompilation, and then yeah, those are extra PRs against R2A and rather two extras. In rather two extras, there's the R2 SVD, which is the parser that goes through all the specific peripherals for a particular device. And this has been super useful to determine function of different pins on the device. Normally, one has to kind of map those peripherals when you do the memory layout for the device. But with already available SVD, which is the definition of those peripherals, you have those already mapped to the offsets that you need. So in Ghidra, there's the SVD loader, which has been unmaintained for a while. Then again, this is a reality; it's not a criticism. I would love for this alternative to be maintained and more readily available. But in R2 SVD is seeing changes and fixes, and it's being really instrumental for this work. For instance, you can just go to visual mode and do underscore. You can look for UART or any peripheral that comes to mind. And we have also had interactions with the upstream CMC's SVD, which is the parser for these XML files that define the peripherals of the device, and they have been very welcoming, and this is kind of like a kudos slide to them. We have some future improvements that can be interesting for reverse engineering tools, such as, for instance, loading an SVD and already have regions such as internal flash, external flash, EEPROM, and different sections already defined for you, so you don't even have to open the datasheet to put those in. And there's also a kind of a human error in there, because when you define the different regions, if they are not defined correctly, all your disassembly can get really confusing, not to mention the decompilation riddled with errors if those are not well put together. So in conclusion, R2 is top notch if you need to do STM8 analysis. And there has been a lot of bugs fixed with cross-references, disassembly itself, instructions, and fine-tuning for the compiler. For instance, comments on the PDC output that guide the LLMs to make a better job at decompiling a particular C output. And this is just barely scratching the surface with the limited time I had to dedicate to this. There's no fine tuning, no RAG, no kind of throwing assembly and signatures to the LLMs to actually have an even better like informed decisions on how the output should look like. And even with those limitations, they do a pretty decent job at having a decompilation. So with the hardware already more or less figured out, we can jump straight to LLMs and decompilation. And suffice to say that decai.r2.js is deceptively simple. It simply uses curl to carry one of the inference endpoints. In this case, it's the Hugging Face one, and then return the results and present them for you. Um, in principle, how we are doing the compilation for this architecture, and it can work for many others, of course, is using PDC, the pseudo-C decompilation. As you can see, it's full of messy go-tos, like spaghetti code that is a little bit annoying to read. But that's pretty much what the LLMs are good for. You just throw this intermediate pseudo-C into a LLM trained with non-specific, no fine-tuning, no RAG um, inputs. And in this case, we're using where we figure out that Claude from Anthropic is one of the best performing models. And then it generates, with decai minus D, it generates a fairly decent decompilation that already outperforms the one from Ghidra. With a few more tweaks, we can see that it even kind of comments, and those comments also come from different steps on the pipeline, and also as you can see the calls, the arguments for the function are also fixed up, and this is thanks to decay minus S, which essentially rewrites the function signature and arguments and even types. And that's something that we can do today with LLMs. So if you are unsure of which calling convention your architecture is using, we can try. It's not always 100% good or for sure, but we can try with LLMs and figure those signatures for you. So eventually, I would like to see this dream of mine turn reality, which is essentially have a device that dumps STM8 with automated glitching because I've been really lucky with my hardware. It doesn't have read-out protection or ROP, not to be confused with return-oriented programming. Nothing to do with that. It's just that the reading out of the flash is in some devices protected, and you need to do glitching to retrieve that flash. Not in this case, but it can be like pretty common in consumer devices that they actually lock it. And there hasn't been in the ST microelectronics standard SDK. It would be fantastic to just like get all the standard library and have it as signatures or a freer database that can inform further on the decompilation front, and then imagine that all these LLMs spit actual C project files with all the different functions, and then after a few tweaks, you suddenly have a freed device that you have source code for. Because essentially those microcontrollers, they have limited amount of functions, so it's not a really complex operating system that you have to that you have a lot of freedom. Here you are pretty constrained by the peripherals and features and limitations that those microcontrollers have. So um, once the LLMs have presumably seen quite a few instances of how to read, let's say, an ADC or generate a PWM signal or initialize a UART, they should be capable of outputting a correct C code that you can just compile right away out of the LLM. And then you have from binary to C project file with including a make file on it, all together. This is a dream. This is not real today, but from what I've seen while working in this project, I don't see this out of the realm of real possibility. And last but not least, I would like to extend a proposal or a competition to the audience. If you're really keen into learning more details or finding more bugs on the current work, or just getting interested in general on how this whole assembly to decompilation using AI works, just pop by in the treadmill RE repository that you can access reading that QR code, and file an issue and try to explain how or which commands would you use to move the treadmill motor. And I think that should be fun. And um, if it's well documented and well informed enough, we will consider giving r2con swag to you. So I hope that everyone enjoyed this presentation as much as I did making it. And thank you very much for watching and listening. Goodbye.